Good morning, everybody. My name is Jason. I'm a PhD student from National University of Singapore. Today, I'm going to talk about Capstone, which is a joint work with my colleagues from both the US and University of Cambridge. Traditional computer architectures rely on large number of security extensions for achieving security goals. For example, there are extensions for memory safety, thread safety, sandboxing, as well as virtualization. A large number of security extensions can lead to problems. First of all, software cannot rely on the availability of certain security features because hardware implements different sets of security extensions, and sometimes security extensions might be deprecated after a few years by the vendor. Secondly, it also offers poor interoperability for achieving multiple security goals. For example, it took people special effort to figure out how to make MPK or MPX work with SGX. And even so, sometimes the conclusion is that the extensions simply do not fit very well together. It also took special effort to virtualize all those security extensions. So if you ask the question, why is it so difficult for traditional architectures to achieve multiple security goals? We find that traditional architectures, they all rely on a fixed hierarchy of privilege levels, where the less privileged software needs to go through a central unit, MMU, memory management unit, or MPU, memory protection unit, in order to access a memory. And such units are managed by the more privileged software on the system, such as the OS kernel and the hypervisor. Therefore, it's clear that it actually assumes a central authority to explicitly manage the security policy, which needs to be trusted by the less privileged software. So this is actually quite limiting in terms of expressiveness. And therefore, we also want to look in the direction of how to make memory access trustless, which means that we don't rely on explicit security policies managed by a central trusted authority. Therefore, in this work, we want to look at a unified foundation for trustless memory access. We summarize a total of 4 properties which we deem as necessary for achieving such a goal. We follow those principles to design a new instruction set architecture called Capstone, which through our use case studies, we showed is very expressive enough to support a wide range of security features traditionally provided by security extensions. Before we go into details, let's take a look at the threat model. In the benign scenario, we consider a very general model where we have 2 domains, A and B. A has initial access to the physical memory. After A invokes B, A needs to set aside part of the memory region to allow B to temporarily access. After B returns, B relinquishes access and regains its access. There are a few ways things can go wrong. In the first scenario, after A invokes B, if it becomes malicious, it can just keep accessing B's memory. This can lead to secret leakage, broken integrity, or attacks such as time of share to time of use. The other scenario is after B returns, if B is malicious, it can also just refuse to relinquish its access, leading to denial of service. So it's both a goal and threat model setup. Let's take a look at the details of those properties for achieving such a goal. The first property is exclusive access. After A delegates memory to B, we need B to have a way to know for sure that it has exclusive access to the delegated memory, which means that neither domain A nor any other domain on the system should be allowed to access that delegated memory. The second desirable property is revocable delegation. After A delegates memory to B, we also need A to be able to say at some point that doesn't want B to have access anymore, and how we should make sure that B loses access from that point on. The third desirable property is extensible hierarchy. Not only should we allow A to do this thing to delegate memory to B, we also should allow B to do the same thing. For example, it can delegate part of its memory to domain C, and if at this point A decides to revoke access from B, both B's and C's access should be revoked. The fourth property is secure domain switching. So if we consider the case where domain A needs to preempt B's execution, for example, for some system management reasons, we need to make sure that B's data is still secured even when it's switched out. That means that domain A is still not allowed to access B's delegated memory. After B resumes the execution, B needs to regain its access. So to summarize, we have those 4 properties that are necessary for enabling a trustless unified foundation. The problem is how to actually enforce those through a unified interface. In the interest of time, we're only going to look at the first 2. We look to architectural capabilities as a base idea. If we have a physical memory, we have a capability as a token, which defines information, which encodes information about memory region within the physical memory. as well as access permissions. So the idea is that instead of using raw addresses for accessing memory, we use a capability instead. For this to work, we need to make sure that capabilities are not forgeable, which means any capability is guaranteed to have originated from a legitimate minting operation. We also need to make sure that operations we can perform on capabilities are monotonic. So if at time t0 we have a capability that doesn't grant us certain access, we can't gain that access by simply performing certain operations on that capability. So if you look at how to enforce this first property, we find that initially domain A will have a capability that grants it access to the physical memory. After A delegates memory to B, B also gets a corresponding capability that grants it access to delegating memory. However, nothing actually prevents a malicious domain A from holding the original capability. That also grants it access to the delegating memory. And in fact, domain A can even just delegate the same memory to more domains by simply passing more copies of the same capability. Therefore, it's clear that we actually need something more than just architecture capabilities to enforce exclusive access. For this, we look to linear capabilities, which is a special type of capability that is guaranteed to not overlap with other capabilities. So very naturally provides exclusive access if held by inside the register file. Because of the special property, a linear capability also needs a special set of operations that can be performed on them. So for example, a linear capability can't be duplicated, can only be moved around from location A to location B. A linear capability can also be delinearized, which will convert it into a nonlinear capability that from this point on can overlap with other capabilities. If we look back at the memory delegation example and see how it works with linear capabilities, domain A initially will have a linear capability that grants it access. It can then split the capability into two disjoint parts, and then it can pass to domain B one of them. Upon receiving this linear capability, domain B can know that it has exclusive access. The problem here is that if domain B is malicious, how can A know that it will ever be able to get back the linear capability? So this brings us to our solution to the second property, which is revocable delegation. Before passing the linear capability to domain B, domain A can first create a corresponding revocation capability, which is a special type of capability that doesn't grant A direct access to that memory region, but instead only serves as token for later revocation operations. So after doing this, domain A passes the linear capability to domain B. And if domain A wants to get back the linear capability, it can perform a revocation operation on the revocation capability, which will convert the revocation capability back into the original linear capability, and at the same time destroys domain B's copy, thereby maintaining the property of the linear capability. There's one problem here, however, which is that secret leakage can happen. If domain B decides to write some secrets inside that memory region, a malicious domain A can actually use revocation to gain access to its secrets. So we actually need to find a way to prevent secret leakage while still allowing revocation. To solve this problem, instead of giving back a linear capability to domain A as a result of revocation, we only give it an uninitialized capability, which only grants write-only access until the memory region has been fully overwritten, so it can protect the original content inside that memory region. So here, as I mentioned earlier, in the interest of time, I only talk about the first two properties. If you want to know about the third and the fourth properties, please take a look at the paper. Putting it together, we get a new instruction set architecture design called Capstone, which defines a set of capability types and instructions. And here's just an overview of the capability types defined in Capstone and the operations. If you want to know more about the details, please take a look at this website. There's a QR code and the URL here. Now let's just take a brief look at the implementation and evaluation. We have a functional prototype implementation, which includes a library that demonstrates some use cases we have explored in this paper. We also have a simple compiler that takes as input code written in a C-like language. We also have an emulation-based implementation of Capstone that can produce the runtime output. In our first case study, we look at memory safety. We find that spatial memory safety can only be provided by architecture capabilities itself. And by using linear capabilities and revocation, we can also provide temporal memory safety and concurrent thread safety. And what's also interesting to note here is that there's a line to join between certain Rust-like Rust semantics and primitives provided by Capstone. A second case study is a memory allocator in a trustless setting. So the allocator can hold linear capabilities corresponding to allocatable memory and revocation capabilities that correspond to allocated memory. This can allow you to be able to get back the resources it has allocated without allowing it to access the allocated memory region. We also have a scheduler, which is similar. It has instead sealed capabilities, which allow the scheduler to perform context switching without allowing it to access the data inside. And for nestable enclaves, we show that it's possible to set up different kinds of regions. For example, shared buffer using nonlinear capabilities and private memory regions using linear capabilities. And all those memory regions can be set up in an extensible hierarchy of delegation. So it's nestable. So to summarize, we have those capabilities that are shown to cover a wide range of features traditionally provided by security extensions. And takeaway here is that Capstone is highly expressive. We have a preliminary performance evaluation, which is based on a Gen5 simulator, and we modified a simple timing CPU model to implement the part that's most unique in this implementation, which is revocation metadata maintenance. And current preliminary results show an overhead of about 50%. In conclusion, in this work, we look at the unified foundation for trustless memory access. We summarize a total of 4 properties that are required to achieve this goal. We follow those principles to design Capstone, which is a new instruction set architecture based on the idea of capabilities and incorporates core ideas such as linear capabilities and revocation capabilities. Our prototype implementations include a functional emulator, a compiler, and a library. And we demonstrate that Capstone is highly expressive and can support a wide range of security features. So again, I want to say that there's a website for you to learn more about Capstone. If you're interested, please just scan the QR code. That's the end of this talk. Thanks for listening.